going to be from week 1 to week 8. Okay. And be careful with that. It is not week 5 to week 8, rather from week 1 to week 8. However, the emphasis is going to be on week 5 to week 8, right? Because those are the new topics that are there. So we are going to have more. I mean, I could not say more questions from there or something like that, but it's just that, it is good to brush up on some earlier weeks also, like week 1 to 4, because there may be questions from that also. But again, you may expect more questions naturally from the last 4 weeks, meaning from week 5 to week 8, because of the new topics, right? So emphasis in that sense is going to be there. But again, regarding the marking and all, it is mostly uniform. Okay, so it is not that we have given more weightage to questions coming from week 5 to week 8. Rather, the weightage could be uniform. You can expect it to be uniform, but then again, the number of questions are slightly higher, maybe on the on this side, like from week 5 to week 8. That is okay. So the thing is that I will just take on the important topics which are there with respect to quiz 2 and discuss only that today. And then in the coming days, we'll have office hour sessions, of course, will be there. And we'll have one problem solving session also, wherein we'll just take one of the older papers maybe and try to solve that. Okay, so that may be closer to the quiz, not today. Today, I just want to discuss the topics, and then one or two questions if you have, maybe towards the end if time permits. You can take some questions and solve them also in this session itself. Okay. So thing is, with week 1, I think you should be aware of the again the terms that are there, but mostly just go through that. You have to just remember what is what. Okay, the processes and all as usual. The quiz 1 also, I've seen similar questions as well. Regarding J unit, you have to be careful regarding the code based questions, where we give test cases and ask you to figure out which test case uncovers the error, right? So there's some code base given, and there's some issue in the code, essentially some fault, and from among the given options you have to figure out which test case I mean, the test class will be given also, and by reading this you have to understand which test case will be able to uncover the error. Okay, similar to the question that you have seen earlier also. Now on the graph part, I think you should be aware of the coverage criteria, right? Essentially, so most importantly, edge pair coverage and node coverage. We all know how to do that, right? So, but edge coverage, edge pair coverage, and prime path coverage. Yeah, so be careful with that. Practice that also. Cyclomatic complexity also, I think it is coming later, but that is also one part that is there, which you need to be aware of. So we'll discuss that. I think there's something specific from here. Yeah, one thing I just like to show here from here is this thing. Maybe better to keep that in mind. The subsumption graph. Okay, maybe you should go through this one, the graph at least. Remember that. Yeah, the towards and side trip. It's good to remember that, because there may be questions on that. Yeah, this thing and the other one also. This is like just the structural part, right? For data flow, we have another graph which is similar to this, but it shows the data flow coverage criteria also. So that one, if you can take a look at that, no. So and remember that, be useful. Yeah, in this one, I think we've given it now. Def and use, you should be aware, because there might be questions again regarding coverage specifically, right? What covers what. So remember, all def coverage. Okay, there might be a graph, right? So all def coverage is the basic one. If you're doing all uses, then all defs is covered. If you're doing all du paths coverage, then all uses is done, and therefore all defs is also done. So in the coverage criteria, we might have that. We had a graph, right? Subsumption. Yeah. Okay. This one we have added, right? Yeah. So you see this one. And remember one more thing. This is important. Prime path coverage does subsume all du paths. As a consequence of that, what happens? All uses is also subsumed. All defs coverage is also subsumed. So essentially, if you do prime path coverage, even though you're doing a structural graph coverage and not du coverage per se, but still, by the nature of it, prime path does subsume all du paths coverage also. Okay, so be careful with this one. And another thing, another detail that you need to be aware of is that prime path coverage does not subsume edge pair coverage. Okay, why is that? Can anyone tell me if you remember from the earlier session? Why does prime path coverage not subsume?
Right?
Sorry, come again, please.
No, that was that all coverage, I guess, that loop thing. But in prime path we have loops, right? So the thing is, I guess it was something which cannot repeat.
Yeah,
That
yeah,
thing, I
safe
guess.
loops.
in
self
a path.
loops.
Yeah.
Yeah, H pair coverage has self loops. H pair coverage requires you to visit self loops. Okay, so if you have CFG like that, where 5 5 is an edge, you have to cover for 5 5 5 also. That's a valid H pair, and therefore that for that reason only prime path coverage does not subsume H pair, because H pair has that requirement of visiting the self loop. However, if you do visit the self loop in a prime path, that is not possible, because we cannot. That will not be a simple path, and therefore we cannot have that in the prime path coverage. Therefore, the prime path coverage does not subsume H pair coverage. However, prime path coverage does subsume all due path coverage, which is the highest criterion. Therefore, it does subsume all users and all devs as well. Okay, so that part, if you are aware, hopefully it should be okay. Yeah, testing, do one or two examples, okay, and go through that, like due pairs, finding the due pairs, due paths. Remember again, for due paths, do not consider subsumption, okay, and I think that will be mentioned in the questions also. But even if it is not mentioned, okay, do not consider subsumption for that. Subsumption we consider only for the test paths. Okay, due paths are test requirements, even though they are paths, but they are test requirements, right? Similarly for prime paths also, prime paths are test requirements, right? But the reason why in prime path we take the longest is a different reason than subsumption. It is not subsumed, rather it is by the nature of prime path that it is the longest simple path, right? Therefore we take the longest one, but it is not because of subsumption. Okay, subsumption is only for the test paths, and similarly for due paths also you do not consider subsumption. So each due path you give separately. Okay, so if we ask for how many due paths are there for a specific variable, you give all of them, and don't like for example, if you have a due path 1 2 4 and then another due path 1 2 4 5, then both of them you give separately, even though 1 2 4 is part of 1 2 4 5 also, but you give them separately. Okay, however if 1 2 4 5 is a test path, then 1 2 4 cannot be a test path. But in the case of test path, now if the larger test path subsumes something which is part of the another smallest test path, then we do subsume. So that's a different thing. Okay, if you ask for how many minimum number of test paths you require to achieve a particular coverage criterion, then you do subsume and give the minimum number of test paths for a specific criterion. Okay, but that is only for the test paths. Okay, but due paths you give the all of them. You don't separate it out. Okay, so that is one thing. Anything in example? Due path, I think you understand. Yeah, coverage, remember, this one is important. Okay, all defs is each definition at least one use, any use. Okay, pick every definition, go through every definition for that specific variable, and again remember, we'll ask for a specific variable only. Okay, be careful with what that variable is. Might be any variable. Okay, now for that variable, go through every definition of that variable and make sure you have one path that reaches one use at least through that definition. Okay, so definition to use, definition, and if there are four definitions, then you'll have four TRs. Okay, because each definition you have to cover for that same variable, right? So that is, and you have to go through one use. All uses is each definition, which is all possible uses, meaning every definition and every use. So this becomes your DU pairs essentially. Right? You go through every definition again, but each definition is also going through all possible uses, not only one use. Okay, this is like one use, right? Each definition, any use you pick, that is okay. But here all uses saying that for each definition, anyway, each definition is common across these three, right? Each definition you have to go by default. You cannot avoid out the each definition part. Each definition is there, each definition, but then you go to all possible uses for all uses. Okay, now all due paths, and there's a slight distinction between these two which need to be highlighted. Each definition, all possible uses through all possible due paths, meaning in this one we were saying you have to go through all your possible uses, and the way you go to that use is up to you. Maybe there are two paths to reach a one use, right? So assume that there are two uses and there is only one path. There are two paths to reach one use only, right? So then in that case, all uses coverage, you take any path to reach that use is okay. I think we'll have an example. Maybe I'll show an example towards the end also. Okay, but all due path is saying that you again go to all possible uses, similar to all uses, right? But additional condition is all uses through all possible due paths, meaning for all possibilities you have for reaching that particular use, you exercise all of them. Okay, so these are the three criteria in data flow coverage. Is that okay? Any confusion in that, or any question that you'd like to ask in this regard, or otherwise we'll move forward.
You can move forward.
Okay, thanks. Okay, so this is, I think, yeah, some example. uh yeah, that's fine. So program that is there. Data flow is okay. Elementary, see this fundamental graph algorithms and elementary I'm not covering because it is mostly DFS, BFS. Okay, if you want to remember something, you can remember that for both DFS and BFS for an adjacency list representation, the time complexity is the big O. Time complexity is O of the cardinality of the set V, which is the set of vertices, and the cardinality of set E. Okay, so V plus E, or you have that bar that is there, no, for cardinality. So two vertical lines will be there, and then you have V inside of that essentially. So V plus E, right? So for both BFS and DFS. In the case of adjacency list, in case of matrix, adjacency matrix, it will be n square or V square in how many vertices you have squared, that is. Okay, but I think O of V plus E is the efficient one. Okay, I think I'm not going to cover this one. Maybe if you need, we can come back to it and see this terminology and process. I think we've discussed that earlier also in quiz when quiz one was being discussed. Okay. Week 4, yeah, week 4. Remember the integration approaches. Okay, important. So what kind of integration testing approaches are there and what is what? So interface, you understand, module is okay. Right, yeah, the types of interfaces also. Just go through that, remember the definition, and it might be given in a scenario, kind of like a scenario, but you will understand what is what. Okay, so just maybe it could be a matching question also. Yeah, multiple rows on one side, and the other column we have these interfaces, right? Names of the interfaces. So you had a match also. Okay, thing is that scenario will be given, you had a match accordingly, and you should be able to get through it. There should not be any confusion. So just go through the definition, understand what is what. Okay. This is okay. Yeah, test up, test driver again. I request all of you to not get confused on this. Test driver is the caller. It calls. It calls below modules. Okay, so it sits on top. Calls the modules which are lower on the hierarchy, right? And test up is a leaf essentially. It's a leaf. So it is called by a module on top. Okay, so it is a callee. Test up is callee. It is skeletal. Test driver is not a skeletal. Okay, be careful with this. Test driver cannot be a skeletal, right? Because it's actual component, not an actual component from the software perspective, from the program perspective, but this is actual working software itself, right? Test driver is a software, right? The software component might not be part of the same program that we are building. It's a different thing. It's an external program maybe, but that's a working program, right? It's not a skeletal thing. It's not a dummy thing. Whereas test driver is skeletal, it's a dummy module. Okay, be careful with this. Again, with the definitions, yeah, these 5 things are there. So no, not incremental. Actually, increment only under incremental you have top down and bottom up. So that's okay. Sandwich and big bang. Big bang is not incremental by the way. So actually under incremental you have these 3. Big bang is separate. Okay, so essentially, so top down, what happens is you're building from the top down. Okay, so what would you need in that case? So let's say I'm building A first, then I'm building B. So C and D are not built, but I want to check the integration between A and B. So what should I do for C and D? Because A depends on C and D also. So I'll use stub in place of
So
C and D. Go ahead, please.
no, so C and D would be stuff. I was about to say that. So yeah.
Yeah, exactly. Thanks for that. Yeah, so that's what it is mentioned here, right? So I'm just doing a run through. I'm sorry, it's slightly faster because if it is slightly faster, we can come back to it later and discuss that in detail because I have to cover a lot of other things as well. Okay, so essentially, yeah, that's what. So then you build D, for example. So CD were not built, and then you move forward. Maybe in the next step you build D now. So C still you're using stub, but D becomes actual module. Okay. So again, remember stub is on the leaf. Stubs are leaves essentially, or below the top module essentially, right? These are being called by a caller. In this case, caller is A. Caller could be a test driver also. In this case, is being called by A. So the caller is always actual module, be it test driver or a component of the software being developed itself. But it could be a complete. It should be actual, meaning it is a complete working module. It cannot be a stub. Okay. Therefore, test drivers are not stubs. Okay. Like on top. Okay. So this is top down because you're building from the top, so you need something on the bottom. That is how you remember it. But if you're building from the bottom, that is bottom up integration testing, right? Or building or testing from the bottom. So what happens is EFG is there, and you don't have the other middle layer. Essentially, this level is not there. So you want to call EFG, no? EFG is there, but these are being it's supposed to be called by something, right? So what do you use? You use the test driver to call them. So therefore, test driver is a caller. It calls, right? And stubs are calling. So in the case of bottom up integration testing, you would not require stubs, right? Because you're building from the bottom anyway, and test driver is already there. You're calling the test driver will be calling it. So you're calling actual modules in all the cases, right? In the case of test driver, all modules are actual. Okay, there could be stubs also in the case of sandwich, right? So in the case of sandwich approach, it might be that you have both. So sandwich approach requires both. Test stubs, maybe some places you need to use drivers because you want to call from the top, or some places you want to use stubs because something is not ready yet, so you want to use stubs in place of that. So that is one thing. In the case of sandwich, you need both. But in the bottom up approach alone, you just need the test driver. In the top down approach, you just need the stub. Because in the top down approach, you have the top module ready anyway, right? So why would you use a test driver then? Because I already have with me, and A is supposed to call the lower modules essentially. So why would I use the test driver in this case, right? So top down, you're building from the top, so you don't need the test driver. However, if you're building from the bottom up, then you need that. And similarly, if you're building from the bottom, then you don't need the stub. So be careful with this. Okay, what else? Yeah, so this part is okay. I think it's the same thing, right? Yeah. Now, a specification is okay. You can just skim through it. Mm, uh, like sequencing constraints are essentially, uh, on FSM. So this we can discuss, but just go through the definitions one. Okay. I mean, essentially imposing some sort of order of what could be called. Like for example, if a queue is empty, then I'm not supposed to call DQ on that, right? So that imposes a constraint saying that if it is not empty, then you are supposed to call DQ only. Otherwise, you cannot call it, and so on, right? And similarly, if the queue is full, let's say a queue has a capacity of 5 or something like that, so then you're not supposed to call NQ. And similarly for a list also, list having a capacity, let's say, for 5. So if 5 items already there, then you're not supposed to call add before calling delete, something like that. So that's how it is. Yeah, NQ must be, and similarly NQ must be called before DQ, right? That's also one thing. So if nothing is NQ'd, then there's no point in calling DQ to begin with, right? So therefore, that kind of constraint is added. That's how sequencing constraint, right? What could be called first and so on. So this is okay. Yeah, FSM again, the notion of accepting, you need to remember. Uh,
Transitions and states.
yeah, transitions and states. Transition states are okay. Transitions are edges, states are nodes. That is okay. Only thing is precondition, you remember. Okay, so again, I'm mentioning this. Be careful with this. When the precondition is true, when the precondition is true, the transition takes place. When the guard is true, transition takes place. Okay, preconditions are the same as guards. So either it be a precondition or guard, both need to be true in order for the transition to take place. If guard is false, you're not going to take the transition. You're not going to make that transition essentially. Okay, trigger is what caused the transition to take place. I mean, precondition is the condition under which only transition can take place. If that condition is not met, even if the trigger is called, if the precondition is not satisfied, you're not going to make the transition. So in this case, it says elevator should be stationary, which meaning elevator should be speed should be 0, right? Elevator should not be moving. If the elevator is moving, which means speed is greater than 0, in that case, even if I do that trigger, transition will not take place because precondition guard will block it from happening because elevator is moving. So you're not supposed to open the door regardless of whether the user is pressing it or not. Okay. The trigger is a separate thing. Okay, trigger is what causes a transition initiation of that, like the request for transition to take place. Transition is the act of transitioning itself, but precondition is what allows the transition or disallows the transition to happen. It's like a check essentially. Okay, hence precondition. And open door is the transition. So open door is the transition that happens on the trigger of open button being pressed. Okay, and that can only take place the opening of door if the precondition elevator speed is 0. If that is not the case, then even if the trigger happens, precondition will not take place. Okay. Sorry, even if the trigger happens, then the transition will not take place if the precondition is not satisfied. Okay, and there are two states and so on. Yeah, the notion of accepting is important. Be careful with this. So it says I'm going to start with the initial node and end at the final node. If there is a string which you can start from the initial node and follow the transitions according to the string, whatever strings you have, right? Like 101 I have. So let's see if it accepts it. So I am at S1, 1, I go to S4, and then 1, so 0 right after that. So S3 and 1 again. So I end up at S2, which means it is not accepted. How does it get accepted? If I get back to, not get back, get to the final node. The final node may be different. In this case, it is same. It may be different. Okay, the initial and final nodes may be different also. Idea in accepting is that you should start at the initial node and at the final node, similar to a test path. It is not a test path, but that's what it is, right? Accepting, meaning you start from the initial, end at the final. If that string is such that you're doing that, meaning it's the FSM. So, and then again, so some description could be given, FSM could be given, description could be given. You have to figure out which sequences will be given in the options, right? So you have to just check and tell which one will be accepted by the FSM, which one will not be accepted by the FSM. It could be MSQ also. So be careful with that. Okay. Yeah, conditions that must be true for the transition to be taken. Okay, triggering events are essentially what happens. The press of the button causes the transitions to take place, right? The initiator in some sense is the triggering event. That is okay. Yeah, equivalence. Just remember it. Okay. So in FSM and note, because FSM is a graph again, right? So if you do node coverage, what does it mean on FSM? We are doing every state, isn't it? Because in FSM, all nodes are states, representing states. So if you do node coverage, you are executing every state, that is, and the other way around, also vice versa, essentially. So if I say on FSM, executing every state is equivalent to which are the following graph coverage criteria, then you should say executing every state is equivalent to node coverage. Because if you execute every state, it means you have covered all the nodes on the FSM, right? That's what. And similarly for edge coverage is executing every transition. Why? Because edges represent transitions in the case of FSMs, and vice versa. So this way you have to remember this. Okay, edge pair coverage also is a pair of transition, actually transition pair. Okay, so this is there. And data flow coverage, we don't usually define it the usual way. Okay, so maybe I can just go through that, but I think it should be okay. No problem. What else? Yeah, this kind of a code could be given also. So thing is, what you do, you create FSM out of this. Okay, read the code carefully. Create FSM out of this along with the preconditions and triggers and everything. Create FSM. Once the FSM is there, then you can easily answer whatever question it asks for. Okay. Yeah, there are 4 states and so on. So we'll make it in a way that it is easier for you to draw the FSM out of it also, in case we ask code-based questions on FSM. Now this is okay. Uh, right. This is just a classification. You can just remember this. It's not as important. Yeah, just go through that. It might be that there could be a matching question on this. I'm not really sure there would be, but perhaps there can be. Okay. So just that you remember it. Okay. Structural coverage is like, for what? For source code, for design, and I think it is not for specification, right? Or is it for specification also? Yeah, it's for specification also. I think structural coverage is for both, and for design as well. I think, yeah. I think all of them are mapped to all of them in this case. But there could be similar question. Only thing is that just you remember, like for example, we might say FSMs are useful in what? So you map sequencing constraints to that, right? Something like that. Call graphs are used in what? So do data flow coverage, right? And something like that. CFG for structural graph coverage, right? So some similar terms will be there. You have to match it like that. Okay. So for example, CFG, the regular CFG is not part of the data flow coverage, right? For data flow coverage, you need to use annotated CFG or data flow graph, right? Even though it's a CFG only, but you have to have annotation on top of it. Then only you can do data flow. Because if you don't have information about the variable, how do you do defs and uses? Then CFGs with defs and uses is data flow coverage actually, right? Because you need this CFG to do data flow, right? So this matching is something that you may want to remember. Yeah, classical coverage criteria, I'll just mention it was in week 4. So from here, remember this. Okay, remember this carefully. Okay, because it might be important. There might be matching questions on this. Okay. So idea is that what we are doing again, just to give you a analogy to remember. See, these statements that are there, right? Code coverage, cyclomatic complexity, data flow testing, decision part. Some of which are, some modification of earlier what do you call, earlier techniques that used to be there, right? Or some terms earlier, traditional terms that were there, now being referred to, code coverage in some categories, some classifications there, right? So from earlier, meaning traditional terminology that are there for source code. Okay, so just remember what is what. So for example, cyclomatic complexity is useful for basis path testing. This is also like one of the older techniques. Okay, structural testing or basis path testing. Okay, now data flow testing is data flow coverage. That is okay. Decision to decision path is anyway traditional one. Code coverage. So code coverage is having multiple of them. Okay, the older ones. One thing is statement coverage, right? Branch coverage. Like for example, in structural graph coverage criteria, branch coverage is edge coverage is equivalent to doing branch coverage, right? And you have decision coverage, which is also separate. and you have MCDC as well. Remember, MCDC is equivalent to active clause coverage in our case. Logic coverage criteria has that, no? Yeah, this one. You see, node coverage is statement coverage, edge coverage is branch coverage, prime path coverage is loop coverage, and so on. Similarly, for logic decision coverage and MCDC, actually MCDC is equivalent to active clause coverage. I think we might have mentioned it here somewhere. Mm, Did we?
In the logical testing slide, it's there. I think
Oh,
so.
in the logical system slide we mentioned, right? Yeah, I remember we had mentioned it. Okay. So yeah, exactly. So that's what. So you have to map accordingly. What else? Cyclomatic complexity, subtrimetric. Yeah, remember cyclomatic complexity is the same as linearly independent path. Okay. So if we ask how many linearly independent paths are there, you have to give cyclomatic complexity. If we ask what is the cyclomatic complexity, you have to give the number of linearly independent paths. Now remember, you want to test, not test, you want to calculate the number of linearly independent paths, then you use this formula. And generally, for most of the graphs that we give, I mean, there might be, in case, so assume that there's a visual graph that is given, like there's an image. Even if there's no image from the edge, you draw that, no? From the edge set. So you have set of vertices, you have set of edges, you draw that. Now, if you see there's a disconnected component, what does it mean for component to be disconnected? Disconnected means completely disconnected. Okay. Don't think of the directed edge and undirected edge. Don't get confused with that. Okay. Disconnected means completely disconnected. Like there's no way to reach it. And therefore, we won't see it generally, disconnected components in such cases, right? For programs. But even if it is there, so you have to have this P as how many number of connected components you have. So let's say you have two disjoint components in that graph. So two subgraphs, like in that big graph, if you draw that and you see that is the case, then you have P equal to 2. Okay. However, in general, it will be one component only. So therefore, you can safely give P as 1. So essentially, the formula becomes E minus n plus 2. That is because P is assumed to be number 1. I mean, assigned to 1. What else? Yeah, that's what it is saying, right? So if in case cyclomatic complexity, if it's a single program, that is, it is already connected. So because you remember what happens is if something is unreachable, then generally the compilers complain saying that you have unreachable code. Let's say you are returning. So for example, think of a method. Okay, in a method I'm doing something and returning, and after that I'm doing something. So it'll immediately complain saying that you have unreachable code because if you return whatever you return, whatever you write after the return statement is not going to be reached, right? Because the function will exit before that. So therefore it'll complain that way. So essentially, and that's how it maps. And then there are other cases also wherein we can see that. Idea is that in general it could be 1. So P, the number of components, will be equal to 1. We can just give that. So this becomes the formula. M equal to E minus n plus 2P. E being the number of edges, N being the number of vertices or nodes. Okay, and there is another formula. If you want to use that, you use that. I would suggest you use this one only. Be consistent with that. But both will give you the same number. Okay, so one way to check if you're doing right is to do both ways and check if both are giving you the same number. Okay. So it says cyclomatic complexity of any structured program with only one entrance point, which generally will be the case, and one exit point. This is important, however. Only one initial node and only one final node. Then the cyclomatic complexity is also equal to the number of decision points, right? So you see outgoing degree 2, that is outgoing. So for the nodes, outgoing degree 2 is there, no? So 1, 2, 2 decision vertices are plus 1. So 2 plus 1 is 3. That's what we get. And similarly for the other formula also, we get it as 3. So this is what we have. Right. So this you remember. Strongly connected component is fine. Yeah, the DD path, I just want to take a few minutes and clarify certain things here. See, first of all, DD path. So you go to DD path and then come to the notion of chain. Okay. See, DD path, what could be a DD path? Okay. And there's some sort of order of precedence as well here. Like what is, because one thing may be classified into multiple categories here. Okay. So sometimes you get confused as to which category we take it under, right? That's one. So I'll just explain in the case of chain, it happens usually. So I'll mention it. See, initial vertex is always going to be taken as one independent DD path, always. Okay, so in degree 0, you have maybe multiple initial vertices, all of them you take as individual separate DD paths. Okay, that's what you do. Okay. Now similarly for terminal vertices, how many ever terminal vertices you have, you take it as separately as a DD path, like those individual DD paths. Now, uh, a vertex, if it has, so this is fairly clear, right? All the initial vertices, all the terminal vertices, I take it like just directly you can take it. Now, if there are vertices such that the in degree is greater than or equal to 2, or okay, be careful with this. This is not and, this is or out degree greater than 2, then you take it as a single vertex. Okay, if this happens, this thing. Number 3. This happens, then you take it as a single vertex. If it happens, so in this case, for example, 2 is there, no? So 2 is not having in degree of 2, however, out degree is 2 or greater than or equal to 2. That is, I mean, usually it will not be greater than 2, but it could be greater than 2 also, right? Because x less than 0, x greater than 0, and x equal to 0 are 3 cases, right? So there might be 3 outgoing edges also. Idea is that decision vertices, you take it as a separate thing, so it becomes 2 independently, like this, like this. Because this happens because of condition number 3. And remember, or, okay? It is not saying and, so both need not be greater than or equal to 2. Only one, any one of them is greater than 2, then you take it. Okay. Now, so these three are fairly clear, and this is independent also. There is no overlap also. So now what it could be that it consists of a single vertex with in degree and out degree as 1. Okay, and this maximal chain of length greater than or equal to 1. So idea is that there is some overlap in between the two. So I'll understand. I'll let you know how to handle this case. So what happens is, it says it consists of a single vertex in the degree or degree 1. So it might be that in the graph, it so happens that you've got a vertex which is having in degree 1 and odd degree of 1. And that is it. Like it's not becoming a chain. Like if you think about 5, you see, in degree 1, out degree 1. Right? But 3 also has that condition, right? 3 is also having in degree 1, odd degree 1. So what do? Do you take it under condition number 4? Because condition number 4 says that it's in degree 1, odd degree 1, then you take it separately, right? So 5 is okay because 5 there's no ambiguity in degree 1 or degree 1, so we take it. But what about 3? 3 also satisfies that condition. So here comes the idea of chain. See, if it is a single vertex within degree 1 and odd degree 1 and it is not becoming a chain, specifically maximal chain, okay, then you take it as a single vertex. That's what it says, condition number 4. So similarly for 5, you're taking it, right? But if something becomes a chain, so this single vertex in degree 1 or degree 1 could be multiple vertices also, no? This can happen. So if at the moment it becomes multiple vertices, then you don't consider that in this condition separately, rather you take it as part of one chain. Okay, so that's the precedence that we are talking about. Okay. If this happens to be 2 or more than equal to 1, uh, I mean more than equal to 1 case, I think it will not happen. Generally equal to 1 is this case only. But if it gets more than one vertices in it within degree 1 and out degree 1, and remember this thing, both in degree and out degree as well, then you take the maximal chain and don't count the single vertices separately, meaning in this case 3 4 is there, right? 3 4, so 3 4 is having in degree 1, so this can be considered under condition number 4 also separately. But the moment we see that another connected node is there which is having in degree 1 or degree 1, so we take these two together as one chain which is maximal in this case, and we cannot extend it further anyway, right? So we take it as a maximal chain and not consider 3 and 4 separately. That is only the overlap that is there, and you have to be careful about that. I mean, it's fairly clear, I think. If it is it's because it's a single vertex, right? But the moment it becomes multiple vertices, then it could become a maximal chain. But remember, one more thing is chain. There could be multiple chains, but yeah, take the one which is maximal, always the larger one. Yeah. So let's say a chain in a path is a path in which interior and terminal vertices are distinct. This is important. It should not be a loop. A chain is not a loop. Okay. So you have initial terminal distinct, and all the interior vertices except the initial and terminal have both in degree and odd degree as 1. Okay. So that is just a chain, however. So there could be multiple of them. Okay. It might be that there are multiple. Okay. So, but then you take the one which is maximal. Okay. The largest one. So that's what happens. And this anyway is a separate condition. So this is only for single vertex, by the way. 4. Fifth one is this. Yeah. Any confusion on this? Shall we move forward?
Yes, sir.
Okay, so we will move forward then. Yeah, now comes logic. Yeah, so I'll do some examples also in case it is required. It might be required, but it may not be required also. I don't know. I mean, we have done some examples a lot of them actually in the prior sessions. So maybe can go through that also. But I just wanted to, like, basics is okay to table you anyway, remember. Uh, This is okay. Yeah, coverage criteria. Just remember that, right? What is what, and there will be questions on this actually. So be careful with that. Both are RACC, RICC, meaning active and inactive. CACC. There is no CICC. TACC, RACC, GACC, and GICC and RICC. These are the five. Okay. So be careful with what is what, and accordingly take the TRs. Essentially, we ask for the TRs. Test requirements. Okay, for this, for these ones. So essentially, yeah, determination again. You have to remember. So XOR method, you are okay with that, right? For determination, how do you figure out the condition? XOR method is there. Any confusion in that? You want an example again, or is that okay? Okay, I'm assuming it's okay. In case you need an example, and so we can do that in the. Anyway, we'll do that in the problem solving session once. So it's fine. Yeah, MCDC is same as active class coverage. Be careful with this. Okay. So I think someone pointed that out. So thanks for that. This is in week 5 actually. But it could be there. So if matching question comes or any question pertaining to MCDC comes, you can say that this is actually equivalent to active class coverage. Okay. What else? Yeah, so just remember the conditions and take the TRs accordingly. Okay. It says GSCC says there are no restrictions. Only thing is measure clause must be active. You take the true case, false case. How many ever cases, such cases are there in the entire truth table? Okay. True, false, true, false, true, false. Okay. I mean, how many ever possibilities are there for a specific clause? Again, we'll say which clause we're talking about. Okay. So read that question carefully and answer for that. Now, CACC, one condition is now imposed here. We are saying when you flip the major clause, the predicate must change. If predicate was true, it must become false in the other case. If it was false, when switching for the major clause from false to true, or any value it could be, the values need not be the same. Okay. Meaning the major clause should not be equal to the predicate. That is, if major clause is true, then the predicate must be true. That is not what we're saying. We're just saying they should flip. When we flip the major clause, the predicate must flip. That is all. The value must change. Okay, so that means correlated. Okay, so out of all the GACC pairs, because GACC does not have any restrictions, only thing is it should be active, which is also a condition in CACC, by the way. So some of the GACC pairs, GACC is the largest set, right? Essentially, from among those, some of them will be CACC because for some of those TRs, some of those pairs, essentially flipping the major clause will actually change the value of the predicate. Okay, so those are CACC pairs also. So you take only those. RACC is now saying something about the minor clauses, not for the predicate. Okay, CACC is talking about predicate and not about the minor clauses. So minor clauses may change. Okay, only condition is predicate must change. Minor clauses changing is okay. It must remain active and predicate must change. That is what CACC is saying. RACC is saying not any, it is not saying anything about the predicate, at least the way we have defined it. Okay, and we follow this. Okay, so it is not saying anything about the predicate. It's saying the minor clauses must not change. So it is like GACC, but in GACC, you only consider those which are having the same minor clauses between the true and false values for the major clause. Okay, maybe if we do an example, it will become clear. But hopefully, at this point, all of you have gone through the material and also the sessions. So hopefully, it should make it apparent enough. But that's what happens. So, for example, in the case of RSCC, we have these ones. Okay, 152637. Why? Because A being the major clause, B and C are minor automatically, right? So I cannot take 1 2, even though 1 2 might be a valid GACC pair, but it's not valid CACC pair. Why? By the way, 1 2 anyway we cannot take. I mean, I'm saying 1 6 we cannot take. Why? Because B and C are not same. So in 1 it is true and true. In 6 it is true and false, which is minor clause are changing, right? Even though major clause is going from true to false, that is okay. But minor clauses are changing. So this is not valid for RACC. For CACC, it is valid as long as the predicate is flipping. Is the predicate flipping in 1 6? Yeah, it is, right? 1 comma 6 predicate is flipping. This is a predicate, right? The entire thing. So predicate is flipping. So this is valid CACC also. This is valid GACC, valid CACC 1 comma 6, but not valid RACC. Okay. So that's what. So 1 5 is valid RACC because true true and true true. Similarly for all the other ones. Okay. So this is what happens. Now in the inactive case actually, as per the requirement, there are 4 TRs, not 2. In active class coverage, there were 2, right? Major clause evaluating to true ones and major clause evaluating to false ones, the other case. And there are variants of that, meaning RACC and CACC. That's okay. But on on a basic level, we have two requirements, right? Here we have 4 requirements in inactive itself. We're not talking about restricted or general. I mean, this is the general one anyway. This is generally inactive. Okay. So there are four requirements. What is that requirement? Requirement is the major class evaluates to true and major class evaluates to false. This is the same requirement, right? This requirement was there in active also. The only condition this time we are adding is one case we're grouping it. So one case is with P being true. The value of the predicate is true, and then you are flipping the major class from true to false, and the predicate does not change. Okay, that's why inactive, right? That's how it is inactive. Right? So from major class true to false, predicate remains true is one group. You can think about like that, and the other group is with p equal to false. So major clause again evaluates to true, major clause evaluates to false, p remains false. Okay. So in the question, it might be that out of the four requirements, meaning out of the two pairs, out of the two groups, you might be able to find TR only for one of these two, meaning 1, 2, or 3, 4. Either with p equal to true or with p equal to false or with both. It could be that for some predicates it might be feasible for both p equal to true and p equal to false. That way you can give the TRs. But it might be in some cases that you don't have both, the meaning out of the four only have two, either 1, 2, or 3 for two of the requirements, right? So in that case you say in the options we'll have it, right, that p equal to false has no feasible pair or something similar will be said. If p is equal to false case is not there, then you say p equal to false case is not there, and for p equal to true these are the pair, this is the pair. And similarly and there could be multiple pairs also, so it will be a set. So you can select like that. Okay, for p equal to false it might not be there, or it could be the other way around also. For p equal to false you have feasible pair or feasible pairs, and you give that, but p equal to true there is no case. So you say that p equal to true has no feasible pair, so accordingly it will be option will be there. You have to select it. Check the table, there will be a truth table given. Okay, check it and accordingly answer carefully.
So this is the case for CNF and DNF, right? Like if you try to do inactive clause coverage,
Hmm.
if your predicates are in conjunctive normal form, then like you will end up having one of these will not get satisfied, right? Like predicate will not evaluate to false if the clauses are.
No, not in general. I think, yeah, it does happen. Like there is some sort of correlation there. What you're saying is correct only. What happens is, let's say you have, how do you put it, right? You have a case where, yeah, if you are in CNF, right, then the false case generally is not feasible. That's what happens. Okay.
Yes, sir.
Yeah, if you're completely in CNF, meaning it's a completely consisting of conjunctions only, not no or is there, like no or condition is not there essentially. So in that case,
Yes.
it does happen, right? But again, be careful with this and accordingly answer it because it's better not to take not to make any guesses in this regard, because sometimes what happens is uh, the predicate may get transformed also. We don't know. Maybe there's a code base that is given, right? And there's some operation going on before you check, or before the condition is there, before the if clause is there, let's say. So some if condition is there, no, under that you have predicate, and I say that in the question it is said that you have to do ICC for that method, right? So but thing is that some transformations may be happening before that also. So it might be that the conjunction becomes a disjunction, or you're negating it. So think about De Morgan's law, for example. You have
Yes,
A
yes,
and
sir.
B, and you negate it, right? So it becomes
It
a
turns into or,
disjunction.
right?
Yeah, yeah.
Yeah.
So we have to be careful with. Yeah, at the end of the day, whatever the final predicate you get accordingly, maybe it is safe to say that in the case of conjunctions, it is difficult to get for p equal to false. Because again, it depends what those conjunctions are telling you. Maybe the operands of the conjunction, meaning the clauses or maybe the literals that are there, maybe they are representing some false condition. In the so a could be a equal to 2 is not prime. You see, so a is saying that a equal to, I mean, a is the literal that is saying that 2 is not prime. So it might itself be false, whereas it is in
Right.
the, yeah, it is not negated. However, it could still be false. I mean, that's what I'm saying. So because we cannot assume
All
that if
right.
something is written, it is true unless we evaluate it. You see,
Yes, sir.
it could be false
Okay.
also. So you have to be, because slight intricacy is there. Therefore, I don't want to mention anything there. Just that if you do it the usual way, I think no, it should be okay. The one easy way is to see the active what is that, the determinant, the determination condition, that is p
Yes, sir.
sub a or p
But
sub b, whatever. If it is false, then
if you
you
can
take it,
do it
and
both ways, then it will work out
yeah,
fine. All right.
yeah. Okay, now yeah, so ICC and JCC is the same thing essentially. So this, and there is no CICC. Can anyone tell me at this point why? Why there is no correlated inactive clause coverage?
You
I
don't have
mean,
one
generally is okay.
determinant clause, right?
No. What does correlation say? Correlation says if I change my
The
clause, major
major clause has to change the value.
predicate, yeah, and we are saying it is inactive. What does inactive mean? Inactive mean it cannot change. So if
Yes.
I'm saying it is inactive, then I cannot say it is correlated. Something which is inactive, how can it be correlated, right? So that's why we don't have CICC. Okay, so this is a useful thing to remember. Okay, this way you understand that okay, if it is inactive, then it cannot change. However, when it is active, it may change or may not change also. Okay, but if it is inactive, it may not. I mean, it will not change for sure. So we are sure on that. If it is inactive, okay. But if it is active, then it may or may not change. Therefore, CACC is there. Otherwise, GACC itself would be sufficient, right? Because the GACC says that you have to make it active. Everything is so the is saying that it should be active, right? So generalized active, correlated active, restricted active. So if it is already active, then why do we need correlated active? Because it might be cases there are cases wherein a clause is active but it is not correlated. However, when a clause is inactive, then it cannot be correlated at all. So there is no CICC that way. Okay. If it is active, it may change or it may not change. If it is changing, then that is valid CACC pair. If it is not changing but it is active, it is still valid for GACC. And if the minor clauses are remaining same, then that is RACC. And there might be overlap also. It might be that your GACC set is same as the CACC set is same as the RACC set, or any two between any two. There could be overlaps. Okay, that is okay. What else? Uh, okay. Yeah, this is okay. Some again feasibility. So essentially, it says we can ignore infeasible test requirements, right? So I mentioned about the 4 TRs for inactive case, no? So if only have one pair, then the other pair we ignore. We say that we don't have a because we cannot help it, right? I mean, if it is not there in the truth table, because truth table is exhaustive. Remember that whatever you see in the table is there cannot be any more conditions after that, right? So if you see that there are no pairs there in the truth table, then how can you select it? There is no way to select, and therefore we say there are no feasible pairs. So we ignore that. Maybe 1, 2 you ignore, or 3, 4 you ignore. Either of the two groups, or it might be that both are feasible also. It's possible, depending on the predicate. Okay, what else? Yeah. Remember this subsumption. Okay. So remember one thing: RACC is not subsuming CACC, but it is subsuming GACC. It is subsuming, of course, right? Because go by the definition always. GACC, what it is saying? Clause. The major clause must be active. Take true case and false case. Is that not happening? Restricted. It is of course happening. Whatever happens in general, whatever the TR is for general is happening in restricted also. Restricted is even more restricted as it says, right? But the general case anyway is subsumed, right? So that is okay. But correlated and restricted are not subsuming one another, okay? Essentially, because restricted is not saying anything about the predicate. It's saying that minor clauses must be same. Just that. Okay. Predicate is changing, it's okay. If it is not changing, it's also okay. But minor clauses must be same. Correlated is saying a different thing. It's saying that if minor clauses are changing, it's okay. Just that predicate must change. Okay. So that is valid. CACC. So therefore it is. But general is subsumed by both. Okay. So correlated subsumes general, restricted subsumes general. Because this is like specialized cases of the general active clause coverage only, right? So generalized is anyway subsumed. I think the arrow is missing here, but you might assume that correlated is having outgoing arrow to general, and restricted separately is going out has an outgoing arrow to general separately. Okay, so that's what you have. And all these active clause coverage criteria subsume CC is just class coverage. That is okay. And the only thing that subsume predicate coverage, remember this, subsumes, because restricted is not insisting on that. If it is happening, it's okay. It's a nice to have, right? So predicate is flipping, it is okay. And minor clauses are same. Predicate is flipping also. It's good. But if it is not flipping also, RACC is satisfied, right? So therefore, in general, it does not subsume predicate coverage. General active clause coverage also, it says you take everything. Make it active, take every possible pair. That is okay. So we don't care about whether the predicate changes or not. So therefore, it cannot subsume in general. However, correlated is specifically insisting on the fact that it must change. If it is not changing, then that is not valid even for CACC. Right? Therefore, by definition, it subsumes predicate coverage because it's saying it should change, right? So it will cover for it. Right? That's what. What else? Restricted similarly is not subsuming predicate coverage, and general inactive class coverage is actually it does subsume. Why? Can anyone tell me why it does? I mean, in practice, it may not do. In practice, it may not do, but theoretically, as it is defined, it does as it is defined. So therefore, some requirements are infeasible, and therefore you're not able to do. But by definition, it does, right? Because we have four requirements saying that p equal to true and p equal to false. Both cases are covered, right? This is the RICC and GICC also similar thing, right? P equal to true, p equal to false. Four cases, right? Two pairs each. I mean, two pairs of four. Total. There are four conditions, right? So there are two groups. So with p equal to true, p equal to false. So it will subsume, right? So therefore, GICC does subsume predicate coverage. Okay. Yeah, I think we've been discussing on this for somewhat uh, quite some time. Okay. Now we have this. I'm not going to go into XOR. Maybe we'll do an example later. So how do you get that condition? Remember, you have to always get that condition, even for ICC. Okay, because you get that condition only then you make it false, right? I mean, only then you realize when it is false and then you take the pair, right? So to both for active and inactive, you have to figure out that condition, meaning you have to use the XOR method to get the condition. We have discussed that in one of the earlier sessions. So you can go through that also if needed. Okay, this is I think for ICC example. Yeah, FSM. Just take a look at the specification. Maybe you can just skim through it. Yeah, remember conjunctive normal form and disjunctive normal form. There might be questions on this. Very important to remember. Okay. So conjunctive normal form, the form is, and this is a normal form, right? So it must be in that, completely in that form. See, one predicate, if it is in some form, then it needs to be completely in that form. Okay, or it is completely in the other form, like CNF or DNF. But if it is a mix of both, then it is neither. It can happen, right? So be careful with that. So in this case, it is conjunctive. Why? Because the clauses are a disjunction. Clauses are a disjunction, or it could be a normal clause or literal also. But if there is a clause with a group of literals which are there, then it must be a disjunction. That is a condition for conjunctive normal form, and the clauses must be a conjunct. Having a conjunction. So it's a conjunct of, it's a conjunction of disjunctions. That is okay. Therefore, conjunctive normal form. We have having a and of ors. Multiple ors are there, and we are anding them together. So it's an and of ors. However, the DNF is the other way around. That is okay. Yeah, DNF is the other way around. It's a disjunction of conjunctions. So the clause is in the internal, the internal, what do you call this? The internal literals that are there, no, they are in conjunction, okay? And on the outside you have or, okay? So it's a or disjunction of conjunctions. That's how you remember it. And if anything flips, so for example, this consider this highlighted portion. Okay? Now I just go here B1, B2, B3 and flip this. So B1 or B2 and B3. So what will happen? This entire thing will become neither DNF nor CNF. Okay, because CNF restricts it, and DNF also. The clauses must strictly be in conjunction in the case of DNF, and on the outside you should have or I could have this case also, no, A1 and A2 and B1 and B2 and B3. So again it is nothing. I mean it is neither CNF nor DNF. This is not in any normal form. Okay, so be careful with this one. What else? Let's make it smaller maybe. And there's some program wherein we are doing some checks. Okay, FSM might not be very important. Actually, what we do is, this preconditions and all, we create predicates out of it. Okay, essentially, that's what we do, and then do the logical coverage criteria over them because it's a predicate again, no, the preconditions and guards. So we make the conditions like that, like major clause again, true, false, take the pairs. So similar to how you do it for programs, just that you take the preconditions. Okay, summary. Yeah, one more thing is important to remember in a clause. So if a predicate is there, how many possible valuations are there? Can anyone tell me? You know what valuations are, right? Valuation is an assignment. So I have a, let's say A or B or C, right? So assignment could be true, true, false, or true, false, true, or so the entire truth table essentially. Truth table is a list of valuations for the predicate, and the predicate either becomes true or false. and so on. So for every literal, you assign a value true, false, and so on. And do all combinations. Right? So these are the valuations. So how many total possible valuations are there for any given predicate?
So you
Let's.
said it's three. So let's say we have three clauses A, B, C,
Mhm.
and each can take two values. So two into two into two. So 2 raised to 3 for
Correct, correct.
three
So in
cases.
general, for n clauses, you have to put n possible assignments. Okay, so remember this.
Yeah.
Okay. All right. Mm, transformation is. I mean, you might just skim through it. Is okay. I think. Right. Yeah. Then we come to symbolic. Symbolic. Yeah. Few things you have to remember. Okay. So many tabs open. So one thing I could do is I could just move this thing there, and
Just a
then.
question. Can we get questions like theoretical question? Because symbolic testing, I think most questions which are logical, which could be question based. Let's say, can we reach that particular line? What should be the case or something like that? Are
Right.
we
Right.
getting?
Exactly. So
Uh-huh.
this we'll get, right. We'll get a code fragment. Generally we'll give you a code fragment. There might be theoretical questions also, because we know the working, right? We know the working of the symbolic testing algorithm, or the symbolic testing technique. We know what is the idea behind it, how it works, and so on. So there might be possibly few theoretical questions also. But in general, we give you inputs like this, like not test cases, code fragments like this, and ask questions based on that. So essentially, maybe this kind of program is given and you want to reach something, let's say, yeah, similar pattern, right? So you have, how do I reach line number 8, for example, right? What could be the path condition for that, or path constraint for that? So then you give that from amongst the option you check, and so on. Okay. So one thing that one needs to remember, so the general notation we know, right, for the condition. So for example, this is the condition 2y equal to, so if 2y equal to x, so first condition, because I know z is 2y essentially, because it comes as y, goes into twice, it becomes 2y, it comes back. So if z equal to x, meaning 2y equal to x, right? So this condition, first condition, becomes 2y equal to x, and so both things happen, should happen, right? First one should be true, and line number 7, this should be true also. So x not greater than y not plus 10. If both happens, then I reach there, right? So this is like one path condition. Like we can read through it and understand, but be careful with whatever transformations are happening in between. Okay, like you have to do all that. You cannot just directly jump into the condition. Meaning in this case it is happening twice of y, but it could be anything. Okay, it could be subtraction. It could make it 0. It could do anything. Okay, and then again your condition would depend on that, the prior value. So make sure you do the entirety of that. Like when you're tracing the program, you do the all the operations that are happening. In this case, it is just 2y, but other things could be happening also. Okay, so the general notation is clear to us. This is the condition like a predicate, right? And then we say and. Why and? Because nested if, right? First if and the next if. So both ifs are true, then only we reach there, so on. This is the general notation. The only notation which might be difficult to understand sometimes is, yeah, and before getting there, one thing I just like to mention. So in the case of, okay, I'll get to, yeah, maybe I'll just clarify that part. So when you get to any condition, right, there are two path conditions that are generated. That's the way it works. So remember this. Okay. One case is for the true for this branch, not the true, rather the affirmation. We call it the affirmation. Affirmation meaning it might not be, it is not in terms of the value of the true being true or false. Affirmation says whatever the condition is, if z not equal to x is the condition, then z not equal to x is true, right? So that's the affirmation of whatever is there. So if the condition, so one is the true case, the affirmation, the other case is the negation. Okay, so two path conditions are always generated for all the decisions that are there. So the first decision, you'll have two cases here, right? Z equal to x and z not equal to x. So two path conditions are there. Now if z not equal to x, then you don't even go and check this one. So that's only one condition, right? If z equal to x, then you move forward. If you move forward, then there are two possibilities here in line number 7. Either x greater than equal to y not plus 10, x not greater than y not plus 10, or x not less than equal to y not plus 10. So the other condition. So two conditions here. So essentially three possibilities are there. Okay, so the symbolic execution, what it does, always there are two path conditions that are generated at each of the statements that are there. Each of the if statements that are there, right? Two possibilities. Okay, so for example, this is the first case. The other case could be not equal to x. So in that case, you'll not have the other thing because you don't go inside, right? So not equal to x. And for this one, you have, this is one case. The other case is x not. I think there's a typo here. This is x not. X not less than equal to y not plus 10. Okay. So the other one, there are three cases. Yeah, these are the three, right? So one thing is the first one is false. The other case is the first one is true, but the next one is false. So this case, all both are true. So if both are true here, so you get to the error. Okay, like that. So two path conditions are generated, and remember the other one is always the negation of the other one. Essentially, yeah, two of them, right? So then branch is one. The else branch is not of whatever you have. So I say x equal to 10, then you go inside. So that is the then branch, right? So x not equal to 10 is the the other else branch, which is not of the condition. You do a negation on that to get the other case. Okay, now the thing is, yeah, with loops you have to be careful. Okay, so this kind of a code statement could be given. Okay, and we can ask what is the path condition for. And remember, this is like a infinite loop, right? There's no stopping condition. How do you stop? Because you keep getting input. You get the input, you check for it is greater than zero, or it could be any other condition also. You check for some condition, do some operation, and then again take the input. So then again you come back, again you check, and again you do some operation, and then again you ask for input, right? So this way it is infinite. So generally the way we ask this in the case of symbolic, because symbolic execution is a program, right? It's a program that is driving another program. So we need a way to stop, because the program cannot figure out on its own how to stop, right? In this case, because it's infinite, we don't know when to stop, right? So therefore we ask generally in this way. For loops, this is the notation. Any loop that could be there. Could be do loop, while loop, for loop. Okay. We say what could be the condition? Draw, give me a path condition for a loop. The sequence of n trues, meaning n times I want to go into the then branch. N times then should happen. And n plus one time else should happen, or false. So true n times true, and then the last time false, so you exit, right? Because you have to exit. Because if you do keep doing true here, so you keep coming back here. But you want to exit also. So you have to have the false case also. So generally we ask like this. So this is the notation. This and over, this is like summation, right? So and over I belonging to 1 to n is the interval inclusive. This is inclusive, okay? And I greater than 0. So that many times, how many times? N times, right? N numbers I need such that it is satisfying the condition. And the last one, n plus 1, n plus 1th number, that is, right? That is the negation. So that should be such that it is false. The condition is false, so that I exit. Okay, now you have to be careful about the interval, because we can ask about this. The question mostly it is like similar. Okay, but the thing is that this interval may change, so you have to be careful about that. If you start from 0 and 0 comma n, how many numbers are there? How many numbers are there in the interval 0 comma n? Or 0 comma 5, for example. If it is 0 comma 5, how many numbers are there?
0 to 5, there are five numbers, including
No,
0.
no, there are six. No, 0, 1,
Uh,
2, 3, 4, 5, 6 numbers, right? That's what.
6, correct. 6,
Yeah,
right.
I
Including
think you
zero
have to,
6.
including 0, 6, yes. And including, of course, it is always, this is a square bracket. This is not round. So in mathematical
Closed
notation, we will,
interval.
yeah, this is closed interval. So it's not open interval. Therefore, you take the endpoints also. So if we say I belonging to 1 to n, how many numbers are there? N numbers are there. And n different numbers are there. Because I 1 to n is like, that many numbers. So 0 to 5, there are six numbers. 1 to 5, five numbers, right? 1 to 5, 1 comma 5, 1, 2, 3, 4, 5, five numbers are there. So five numbers, five different numbers I need. Ni, right? This is the the first n, the second n, the third n, the fourth n, the fifth n, such that it is greater than 0, so that I go to the then branch. If the condition is true, I go inside the loop. I do iteration. The loop is run, right? And finally, and again, and finally, the n plus 1th. So whatever is the last, the endpoint of the the endpoint of this interval, because that many times you want to make it true, right? That is okay. After that, plus one of that, it could be any interval. We could get it arbitrarily. It could be anything. Okay. We try to make it generally easy, but it could be any interval. The idea is that how many things are there in that interval, that you have to be careful about. Okay. So when we say n times, you want to make it true, then you make sure that there are n unique numbers that are there, so that n times it is true. And for the last time, the endpoint of the interval plus one, the sixth. So if it is 5, then for the sixth time I want to get a value such that it is false, so I exit. Okay, now if it is 0 comma n, what will happen to the other thing? N it will become, right? This plus 1 you don't need then, because 0 to 5. So for 0 it will go inside, for 1 it will go inside, for 2 it will go inside, for 3 it will go inside, for 4 it will go inside, and for 5 it will go inside, right? And for 6, which is n, that is the last one, n sub n, this one. And so for the for the sixth value, that is, which is 5 actually, because we are starting from 0, right? The actual value is 5, but you know the the number of that number is essentially the instance is 6, the sixth number, that is okay, is a negation. So however you go inside, the negation of that you will take you outside of the loop, like exit the loop, right? So you take the negation. So if it is greater than equal to 0, then the negation will become less than. If this true case is less than, for example, for some loop, right, then you negate it, get the other case. Okay, that's how. And we ask generally this, like how many times you want to make it true, and followed by a false. Followed by a false meaning you want to exit, right? So because if you don't exit, you keep going forever, but you have to exit, right? So therefore the false condition at the end. Okay. So that is one kind of question we must ask. Be careful with this notation. And another kind of question we may ask is, so remember this loop is going on at the end, and remember the sigma we are mapping, no? You remember sigma from the earlier discussion that we had regarding symbolic execution, right? We map every variable to its current value and so on. We keep looping over that. So uh, at the end of the execution, it is asking again a matter of understanding the intervals correctly, right? What is the state? Meaning, what is the value of n at the end of the interval, and what is the value of the sum? Because why? Because in the code you had that, right? In the code, it could be something else also. It could be product. It could be anything. Could be a product also. Condition could be anything, even or odd. It could be any condition. I don't know. Okay. Accordingly, you give that. But you have to be careful about this. So now it is saying at the end of the execution, what is the state? Meaning, what are the variables holding at the end? So the loop is finished. What is the value for each of those variables that are there? So sum, remember how many times we went inside, because sum is only happening when we go inside, right? While n greater than 0, we go inside is sum, right? So we went inside in this interval, right? 1 comma n, right? This is that these many times we went inside. So the summation will, the interval for summation will also be the same thing, right? I belonging to 1 to n, because these many times we went inside 1 to n, not n plus 1. Okay. And but the value for n is the last value with which we exited, because for the last time also you accepted the input, right? Assume this is the last sum. So for this, for 5 times you want to do it 6 times, right? So this is the 5th time you are doing sum, and the 6th time you want to exit, right? The 6th time you want to exit it. So you take input again. So this is the 6th value, n6, that is, right? And you check it is false. So you don't sum again, you exit. So the last check is also happening, no? Then only you exit it, right? So the value, the n, that is the value for the n variable is actually the n plus 1 with which we exited. That's how we remember it. Okay. So the sum is for how many ever times you go inside the loop, because then only you sum. But the value for n at the end of the execution is the last one with which you exited, right? Because you checked and then only you exited, right? So it will hold the n plus 1, not until n. Okay. Be careful with that. And the notation, the name of the variables may change. It may be some other m or anything. Okay. But we have to be careful about the general idea. Is that okay? Any confusion in this? Um, okay, so I'm assuming it's fine. Yeah, go ahead, please. Whoever is trying to ask.
It is fine. It is fine.
Okay, okay, thanks. No, I'm not looking at the meet window actually. Therefore, I'm not seeing the reaction. Sorry about that. Okay. Yeah. So yeah. Continuing from symbolic execution. See, symbolic execution. It does the thing completely symbolically. Completely symbolically. There is no concrete value. Okay, everything in terms of path conditions and constraints and variables, symbolic values, right? X naught, Y naught, could be anything. N naught, J naught, K naught, could be anything, right? But no concrete value, as in actual values are not there, right? But concolic execution, what happens is concolic testing, it does concrete plus symbolic. So some parts of the program it drives symbolically, similar to symbolic execution. But some parts of it, it gives actual concrete values, similar to your test cases, test inputs, right? We give it, right? 1, 2, 3, 4, or whatever. Like actual values, right? Y is there, so we give values. It could be anything, 22, 7. We give that value, right? So that is concrete. So it does both. Why? In order to alleviate some disadvantages. So yeah, it's important to understand this. So generally in symbolic, this is like complete symbolic execution, right? Like only that, no concrete execution. Okay. So problem is that if the path condition is there, that cannot be solved by any constraint solver. And again, we had done a detailed discussion that in the previous session, so you might go to that also in case you need more context in that. But essentially, what it says is we get the formula, right? If we cannot solve it to get actual values, we cannot generate test cases, right? Because at the end of the day, we have to give actual values, right? So what we do is we get the PC, we pass it to a solver. The solver gives us actual values such that that condition is satisfied, right? So we pass it to as a test case, and the program is run on the same path. The execution path is same because it maps to those conditions, right? Essentially. So if it is cannot be solved for any reason, and there are various reasons, we discussed that. So in that case, it cannot be done. Like symbolic testing cannot be done. The other is that, and this is more practical, you might be able to relate to it. We want to test something, but some code is not there. Think of network client server applications, or these days very common, right? Web based applications. You have not the entire thing is not there with you. Maybe client side is there, but what about the server side? You don't have the entire code, right? You're making API calls. Some call is given and going, and then only you get the result. So if it is symbolic, how do you get the result? Like how do you proceed? You're stuck there. You're stuck there if you don't have the code, right? So to alleviate this particular disadvantage, especially number two, there is this concolic testing approach, which does both. So wherever symbolic execution alone is not possible, we give random input there and proceed. Okay, the rest of the code we drive symbolically. That's how we do. And the other thing is that in many programs, think of operating systems or web browsers or very huge programs, right? Number of paths, possible paths are quite like very huge essentially. Okay, it's like it's not feasible to do all the paths. Okay, so this is general enough. So what we do, we put a limit. We say we are going to go up to depth of some depth, k depth. Okay, so let's say we are going to go to depth 30 or something, and then only until that we test and then come back up. Okay. Otherwise, we keep going, right? So concolic testing, what it does, symbolic we have seen how it does. We trace the program and collect the path constraints. Okay, solve them, and whatever input you get, you give that to the as a test case, and give that to the program, and you follow the same path. In the case of concolic, what happens? Case of concolic is that you start with a random input. That's the distinction. Okay, concolic starts with a random input, any input. We know what inputs are, like it's integer, right? So you generate a random input and executes the program both concretely and symbolically. We are doing both concolic, right? Concrete plus symbolic. So what we do, we observe what happened on that input. Like 22.7 was given, and I think we are talking about this program only. So it's good to open that. Yeah, this program is there, right? Twice one, yeah. So this one, if you see, right? So 22.7, we run on that on the random input here. We see what happens with the first one. So it turns out z not equal to x happened. Like we trace the program completely, and we say x not equal to 2a not happened. So concrete execution has taken the else branch. We know that. Okay. So we get this path constraint. Now whatever the path constraint is according to whatever happened. Okay, be careful with this. And we negate this whatever happened to get the other case, because this case is already done, right? I mean, 22.7 is doing this x not equal to y naught. So this case is done. I want to do the other things. I want to drive it to the other branch, some sense, right? So I negate it. I saw what happened. I saw what happened with the condition and accordingly generated the other case by negating it. So I negated that and got the other condition and then solved it. Again, solved it by a constraint solver. Got the other test input. So we started with this test input. We saw what happened. We negated that. We get the other case also. Okay. Next time. So if this for x2 and 1, this happened, right? So again, two path constraints are generated, and this is the first case. Maybe it's a false case, right? So false case, right? It's a greater than, yeah. If x greater than, then we go inside. So less than will be the false case. One case is that it is less than equal to y naught. So we don't go inside, and we negate it again to get the other case, which is. So at every state we are again negating and getting the other case. Only thing is that in concolic we start with a random input, and for this execution it is this for the current one, like for 22.7, it is x not equal to 2 y naught. For the next one, okay. For the next execution, we have x not equal to 2 y naught. Okay, so be careful with that. We can say what is the path condition for the current execution. So you give whatever happened with the random input, that condition. But we might also say what is the path condition for the next execution for this one, for this particular predicate, or for this particular if statement, right? So you negate it and give the, because in the next stage, like the next time it is going to negate it, right? So you give that condition. Okay. Uh, yeah. So you have to be careful about that. Is that okay? Yeah. And then maybe we put some limit also in case the number of paths are huge and so on. It's fine. All right. So be careful with the next versus current. Okay. In the case of current execution, we give whatever happened with the random input. We check that. And for the next execution, whatever happened with the random input, negate it. You get the other case. If it were the case that for the random input x naught equal to y naught happened, then you negate it, you get the other case. Okay. So depending on what we ask for. Okay. Dart we can skip for now. It's fine. Yeah. Now week 8. Again for requirements. Yeah. For requirements, be careful with the definitions again. Okay. What is what? Some classification. I will try to make it not so ambiguous. Okay. So you can classify. Some scenario will be given again. Some scenario is there, and you have to classify what is what. This case. So if you are clear with the definitions, I think you should be able to understand it well. Some confusion sometimes comes in the context of business requirement versus user requirement. Maybe in the next session I'll highlight that while solving the question also. And functional versus non-functional. Okay. So for now, I just request you to go through this and remember the definition. Okay, this is for the requirements part. And yeah, with this we come to functional. So up until week 7, it is all code based, right? We know the code. It is white box as we call it because we know the code. It is white box. And some techniques even work on the code, like for example, think of logic coverage criteria or symbolic execution for that matter. Right? We need to know the code, then only it makes sense. Even for graph, structural graph coverage, data flow and all. But functional testing, we are not looking at the code now. It's a black box testing technique, wherein even if we don't know the code, right, we are looking at the program from the outside. So think of a user perspective now. Okay, whatever happens, I don't know the internal. From the outside, I'm looking. Okay, so this way we are going to like what we could do in this case when we don't know the code. Okay, it's white box testing we have seen graphs and all logic, some symbolic, but black box testing is only about input and output because whatever happens inside, I don't know. Okay, I'm putting the input. Is the output whatever I'm getting is expected output is correct or not? We check that. Okay, that's what happens. So essentially, a program is viewed as a function. So the entire program, yeah, it accepts some input. It could be multiple also. So xi and gives you some output, and then you essentially check whether it matches the desired output or the expected output or not. Similar to this case, right? That's what happens. So that's what happens now. Now in the functional testing, we have some categories out of which I think these two pairwise testing cause effect we are not going to discuss. Okay, I think we are not discussing this course, but these four are important to understand. And equivalence class and module analysis are kind of very similar. Okay, and decision tables and random testing are different. So these four we'll look into that. So maybe for today I'll just go through this, and in the next session maybe we can do some questions also. Again, we'll have office hour sessions also, so in case you want to discuss some question or some doubts, you can come there as well. Okay, so what happens is in equivalence class partitioning, if you've done, you know, symbolic execution how it is working, right? So you have one class of inputs, and then it drives the program into another class of inputs, that is another branch, right? So it negates it, goes into the other branch, right? So equivalence class partitioning is something similar. What we are doing is the input domain, we partition it such that one input from each domain, if we do, no, so we are sure that we have done for all the equivalence classes. What it means is, think of even integers and odd integers. I have a program, it checks for whether the given number is even or odd. Okay, so how many equivalence classes could be there? We have one class where the number is odd, or the other class where the number is even. So it does not matter which number it is, you see, because if for even, let's say for the even case, for the even class, I select 10. Okay, so 10, the number 10, x is equal to 10. I selected that, so that is enough, right? Then I need not check for x is equal to 12 or x is equal to 14 or x is equal to 17, right? Because I know that these are the only two partitions. I have checked for the even case, and for the odd case, let's say I select x is equal to 3, so that goes into the odd case. So one number from that odd class and one number from the even class suffices, and we have to check for 0 also. Actually, there are three possibilities, right? Because 0 is neither positive nor negative. So you have x is equal to 0, so that is one case. So three possible partitions are there, equivalence classes are there. So that's how you partition it. So depending on the requirement, we know the requirement from the outside, right? This kind of specification will be there. Now accordingly, you have to figure out how many equivalence classes are there. So generally it depends on the condition, and we have to check for the invalid input also. So I'll mention here. Whatever. So that's why it says all inputs from one subdomain have the same effect in the program. Output will be same. For example, if we talk about even numbers in that same program, then either you provide 2 or 4 or 6 or 8 or 10 or 12, output will be same, right? It will say even. So because in that subdomain, any input you take and that is having the same effect in the program, right? So that's how you divide. So you're dividing essentially. So you see this kind of requirement is given from the outside. Okay, we don't know the code. It says if AGI is between this and this, the tax due is this 22%. If AGI is between this and this, the tax due is 27%. And if AGI is between this and this, the tax due is 30%. So we know if I do one case for 22%, which is like between this interval, then that suffices for that case. Like I've checked it, right? And if I do one case for 27%, then I know that that case is working. I do one case for 30%, that is okay. So there are three equivalence classes. At least we know how many equivalence classes are there. But the thing is that when you do testing, you have to do for invalid input also, right? So for example, you define up until let's say 100 billion, right? It's 100 billion. So what happens beyond 100? Maybe that is not defined or some error at the boundary could be there, right? So that case also we check. Similarly, $1 is given, right? What happens for $0? So negative numbers, right? So we check for that. So as a tester, we have to check for invalid inputs also. So even though these are the given classes, okay, these are the rules. The partitions we get, there are 5 of them. Okay, so this belongs to the valid case, and rather these three, one and these two. These three belong to the valid case, and this the second one and the last one belong to the invalid case. So you have to go for the invalid case also when you have a boundary which is closed, and you know uh, you have to go beyond that also. That is and less than the starting point also, because you need to check for the invalid input, and there might be, depending on the other scenarios, depending on other kinds of situations, you can have other uh, types of invalid cases also. So you consider that also. Okay, like giving invalid like in this case it is a number, right? But it could be invalid string also and something like that. So generally it will be number, I think. But yeah, that's what. So that is what. So what it says equivalence classes, you go to each class and select one thing from that class, one input from that class. That's what we do. That what we do. So you have 3 of them, and then invalid cases also. So one invalid case is less than one, the other invalid case is greater than 100, assuming that these are numbers, right? If you have dynamic types, then that might be a problem. Like for example, if it's a string, right? $100 is a string, then you might need to check for that also. But we are assuming that these are all numbers. If these are numbers, then we have limited cases. Okay, this is okay. Now, so now on equivalence class partitioning, boundary value analysis, what it says is it insists that you must check for the boundaries. Like equivalence class partitioning is not saying that. It's saying that for each class you take one value. It could be close to the boundary, but it could be anywhere. You just take it. But sometimes what happens is boundary value analysis is necessary because the programmer may make mistake at the boundary, and that is general case. Right? Usually it happens that instead of greater than, I wrote greater than equal to, or less than. Instead of writing strictly less than, I wrote less than equal to. Some boundary issues are there. So boundary value analysis on top of equivalence class partitioning, it is saying that you must check for the boundaries, that is at the boundary, near the boundary, and between it. Between it is anyway equivalence class, but boundary value analysis specifically says that near the boundary and on the boundary you must check. Okay, so that is what the condition is. So if you see for this particular equivalence class, the boundary values will be, because this is the boundary, right? So one is on the boundary, less than the boundary, and essentially like little bit above the boundary also. That's what the condition is. And between you have to check also. So essentially 0, which is less than the boundary, on the boundary itself, which is 1, and slightly higher than the boundary, maybe 1. But generally in the case of whole numbers, it will be like close to the boundary. So we might take 2 also, so on. This is how you check. So and similarly for the endpoint also. So you have 29,500, right? So you check for like 29,499.5, or on the boundary itself, like 29,500 and 29,500.5, slightly higher than the boundary also. That's what it says. Okay. So AGI is having these many boundaries, and the boundary value analysis will be according to the boundaries. So I think this is 100 billion actually. So accordingly you increment it. Okay. So actually, a set could be given a set of values, and then you have to understand which is appropriate for boundary value analysis. Again, rules are on the boundary you must check, and you know less than the boundary and more than the boundary. That is like higher than the endpoint, less than the starting point, on the starting point and on the endpoint, and between these two values, between the boundaries essentially. So that becomes equivalence class, but you have to have that as well. Okay. Decision tables. Yeah, decision tables I already discussed in one of the earlier sessions. So if you want, you can go through that. It's fine. Uh, Idea is that what conditions cause what effects to happen in the program. And if repayment amount has been mentioned, for example, then you process that. If it is not mentioned, then you don't process it, and so on. So like conditional. Uh, Again, random testing is just that we test giving random inputs, because the domain is like infinite, right? For example, integer, right? So what do we give? So what we do in random testing is we select a value, compute the whatever the method is, like we do the calculation, and we check for accuracy within a certain bound. If it is coming, if it is coming accurate to that many, how many ever decimal places, or how many ever error we can have in the threshold, that if it is coming within that limit, then we consider that is okay. If it is not, then we correct that, we rectify that method. So that is one way of testing. This is in functional testing. Now the last thing that I'm going to discuss is regarding ISP. Some formula are there, so that needs to be understood. So partition we understand. So partition needs to satisfy two conditions. Okay, any valid partition. Generally, we'll give you a scenario wherein partition will already be given. You have to understand which are the equivalence classes, but essentially the rule is this. Okay, so all partitions must be pairwise disjoint. There should not be any overlap between the partitions pairwise. Okay, and if you take the union, then it should be complete. Meaning, like S is all possible inputs. Okay, then you subset it in such a way that all of them are pairwise disjoint, and the union gives you everything, so nothing is left out. So that is your partition. That's a valid partition. That is okay. Now we have characteristic. That is one attribute. Okay, so let's say person is there. So person's age is one characteristic, and let's say person's income is another characteristic. Right. So both characteristics are having different boundaries, different partitions. Right. So accordingly we check for that and so on. Based on some characteristics, we create the partition. And the idea is that it should be complete and disjoint. This is okay. I'll just give you some examples. So this is like same example we are taking from the previous slide. These are the three uh, rules essentially. So we create these many partitions, 5 partitions like this. And yeah, and you don't need to add two always. Okay, be careful with that. How many ever partitions are there? Just add two to that. That will not work out. Okay, because you have to be careful with the boundary. Here we have a endpoint, right? It might be that if AGI is greater than 58,501, then there is no endpoint, right? So then you don't need to check for that beyond the boundary, because there is no virtually there's no boundary, right? So then the tax due is 30% anyway. So you don't need to check for that. So you don't always add two. You have to check for the boundaries. Okay. If this kind of a closed boundary is there, then you consider the invalid cases, and there might be other invalid cases also. Careful with that. Okay, this is okay. Some theoretical discussion. This all we have discussed in one of the earlier sessions also. So you can go to that and understand it. Uh, yeah. So some of the testing criteria that is there in the case of input space. So assume that input is already partitioned. We have it as a partition. Then what do we select and how do we test? Like the partition is already done. How do we do that then? So it says essentially if you have three partitions like this for all combinations, for example, it's one of those. A, B. So these are like possible inputs, in each characteristic, right? These are like characteristics. So one characteristic could be any characteristic, which is having possible values A, B. Another characteristic possible value 1, 2, 3. Another characteristic value possible values X and Y. So all combinations is we have to do all combinations. So the formula is this: product of all possible, essentially all the value, the product of all blocks, the values in all blocks. So 2 into 3, which is 6 into 2, which is 12. So 12 possible, 12 test cases are required for ACOC, all combinations coverage. Remember this formula, okay? It might be important. Now, and so on. So each, now we have another coverage criteria, which is each choice. Each choice, what it says is, from every partition, you make sure you exercise at least one choice at least once. Every choice at least once. That is. So if you have one test case A1X, right? Then B is not exercised, right? So you have to create a test case for B also. So you could do B1X, right? So that would do for A and B. But 2 is not exercised, you have to create another test case. But remember, we could select any value for the other one also, other test, for the other characteristic, that is. Okay, so if you have A1X, then I can make it B2Y. So that way, these two test cases would do this one completely. Like each choice in that partition is covered, right? A and B are covered. 1 and 2 are covered. 3 is not covered yet. X and Y, however, are covered, right? So X and Y is already done, right? So A1X, A is done, 1 is done. B2Y, B is done and 2 is done. X and Y already done because X is done in the first one, Y is done in the second one. So this partition is already covered. Only thing remaining is 3. So we create A3X. But this, you could have anything else also. You could have B3X also, or you could have B3Y also. Idea is that you should select each possible choice at least once. That's what it says. So the number of possible, the number of minimum test cases that require actually at least these many. How many? Max of the BI. So essentially you have 3. Here you have 3, right? So 2, max of 2, comma 3, comma 2. So 3. You just look at the partitions, give the maximum number. So these many test cases you would require 3 test cases. It suffices. Okay. This is for each choice coverage. So ACOC we have seen, each choice we have seen. Yeah, PWC, pairwise coverage, essentially the formula that is given holds under certain assumption, which does not hold always in all questions. So we'll figure out a way to do this. Maybe I'll discuss during the solving, in the other session when we solve the question. Okay. So essentially you map it pairwise, essentially that's what you do. So you take one thing from here, the other thing from here. So A1, B1 and 1X. So this one map to that one, right? All these pairs you create and then essentially you combine. Okay. So once all of them are covered, then for the remaining ones, you can choose any value. Similar to what happened in this each choice also, right? You had A1X, B2Y. Then if you have 3, because XY and AB already covered, 3 was remaining. So 3 I chose, but A and X I could have chosen anything else also. Right? I just need to cover for 3. Right. So that's how similarly it happens here also. So maybe we do one question, we'll understand how to do this in the next one. T-wise coverage, maybe you can skip it. It's okay. I will ask up until pairwise coverage. Also. We extend it essentially. So instead of selecting combinations of 2, we select 3 and so on. So any number of possible pairings could be there. What else? Yeah, there is one more important one, which is the base choice coverage. Okay, so ACOC is important. All combinations, each choice, pairwise, and then you have base choice. Okay, base choice coverage, what it says is, and this is an interesting one. A base choice will be given, so A1X. Okay. Now we ask for how many total tests are required, so include the base test also. Or we say how many additional tests are required, so you give everything apart from the base choice. So these many. Okay. So how do we do this? What happens is we start with the base choice and each characteristic or attribute we select and vary that only and keep the other ones from the base choice. So let's say A1X is there. So I start with the first characteristic, which is AB, first partition. I mean, yeah, first partition we start with that first characteristic, and I change A to B, but 1 and X I keep from the base choice. Now I reset to the base choice. I come back to the base choice again. Now for AB is covered, I go to this other second one, which is 1, 2, 3. So for 1, 2, 3, I'll then start varying. So 1 is already there for 2, but A and X are coming from where? Coming from base choice. That's how. So whatever you are varying, you would vary that only, and the other characteristics are coming from the base choice. That's how you do base choice coverage. Okay. So A and B are varying, and 1X are coming from base choice. Similarly, 1, 2, 3 is varying here, 1, 2, and 3. But A and X is coming because it is there in the base choice. Okay. And what else is remaining? Now X and Y, right? So X is already there. For Y, you change it, but A and 1 because A and 1 is there in base choice. Okay. So you reset to the base choice and then vary the other attribute. One by one, you do it for all of them. And that's how you get it. The formula is like this. This is for total number of tests. If you ask for additional number of tests, then you subtract 1 from it. So 1 plus summation of bi minus 1. That is how many test cases are required here. So if you come back to partitions, these are the partitions, right? AB 1 to 3 and XY. So for each, go to each block and subtract 1 and sum all of them. So 1, This is 2, right? So minus 1. 1. This is 3. So 2. 1 plus 2 is 3 plus 1. 3 plus 1 is 4, right? So 4, uh, right, 3 plus 1 is 4. So 4 tests are required. Yeah, 4 additional test cases are required for base choice coverage plus 1, the base choice itself, base test case. So you have 5 of them in total. Okay, summation of bi minus 1. So each, you go to each block, subtract 1 from each of them, and then sum them together, add 1 for the, this is for the base choice. Okay, is okay? Make sense? Any questions on this?
Just one question. In the question paper, let's say there is given additional, then
Mm-hmm.
only we don't need to add that extra one before
Mm.
that summation, right?
Yeah, 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 yeah.
So,
In the,
so you see, I saw three questions in three different papers. First
Mhm.
was clearly mentioned that additional base base choice coverage conditions we need to find,
Okay.
given
Additional
the
test.
you know
Okay.
the ISPs.
Mm-hmm.
Then another question we had, it was clearly mentioned that todo fine. So I have to
Total.
add that base case given, which was
Also,
given.
yeah, yeah,
So let's
yeah,
say,
yeah.
but another question earlier today I found nothing was given,
Okay.
and they applied this entire formula. That means that one was added.
Yeah, yeah, yeah. So
So so this
if we don't,
wordplay.
yeah, yeah.
Hmm.
If we don't say anything essentially, then we by default assume that you add it. Okay. But if we specifically
Okay.
say
So
that,
hmm.
yeah, but if we specifically say how many additional tests are needed, then you subtract that one. That is
Okay. 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 So
okay.
if
Okay.
nothing is given, that means we have to add
Total.
that particular base case
Yeah, yeah.
to the number of cases. Okay.
Correct.
Understood.
Correct. Correct.
Yep.
Very nice. Okay. Now MBCC is just an extension of that. I think we'll not be having question on this. Okay, so you can skip that. Essentially, so instead of having one base choice, your base choices themselves are multiplying. So you have multiple base choices now. Like one base choice is there, no? So then I'm doing additional on this. Then I go to another base choice and then do again this thing. Yeah, so it's like a nested thing essentially. But MBCC you can skip that. Now some subsumption. So all combinations, of course, by definition, would do T-wise coverage because all combinations, right? So because T-wise is like how many ever combinations you can make. Not combinations, combinations of that length. Essentially, pairwise says that I take two values from each partition and combine them, right? But you could be having three wise also, meaning instead of selecting two, you could select three at once and combine, right? Like that. So therefore, all combinations coverage subsume T-wise, and T-wise actually because T-wise is extension of pairwise, T-wise subsumes pairwise. MBCC subsumes base choice coverage, and both pairwise and base choice coverage subsume each choice. Each choice is at the base level, and each choice just says every choice, possible choice that you have for every characteristic that you have. How many characteristics are there? Three, right? X, Y, A, B, C, or A, B, 1, 2, 3. Right? So you have to exercise one at least once, two at least once, three at least once, X at least once, Y at least once, and A at least once, and B at least once. That's what each choice is. So you can combine like that and get that. Just guess each choice is the base, like not the base. Essentially, it is it's the most basic coverage criterion, and then on top of it we build. So these three are important. Okay, each choice, base choice, and all combinations. Remember, for all combinations, is just the product of all the all the blocks. Okay. What else? Okay, so I think that covers for this part. Now, in the next one, we can continue on with some questions, like start solving questions also. Okay, so anything else before we close?
Hello, sir.
Yeah, Janvi, go ahead, please. Yes.
Sorry to interrupt.
Mhm,
So I was saying that just now I joined the meet.
mhm,
So
mhm.
could you kind of give the gist of what is being discussed in today's session
Correct, correct.
so
So
that I could
essentially,
watch
correct,
once?
correct. Correct. Essentially, we discussed the syllabus for quiz 2, the exam, upcoming exam. Okay, and went through the important topics there. And this is also being streamed, so this is there. You can go through that again if you want to. But we generally discuss the concepts that are there. Now, in the upcoming sessions, there'll be office hour sessions in between. Like, will be available. We announce it in the evenings. You can have it. And before the exam, possibly on Friday or Saturday, we'll have a problem solving session also. Then we'll do it exclusively just solve problems. Okay, from whatever you have, or
Okay.
maybe some of the PYQs. Okay, but today we just discuss the concepts that are important from week 1 to 8. One important point is the syllabus is from week 1 to week 8 and not from week 5 to week 8. Okay? So be careful with that. So some of the earlier weeks also, like 1 to 4, graph based testing, there might be questions on that. So it is good that if you go through that also. Okay.
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 So one suggestion from my side for the problem solving session or either in the office hours, could you
Mm-hmm.
take up the questions which could cover up the topics or the concepts which we have for the quiz two, especially from week 5 to week 8?
Yeah, yeah, of course we will take it. Yeah, that is the plan actually. We will take those which are aligning with the exam also, so that will help you practice. Right, that's what. Especially, yeah,
Okay, sir.
especially week 5 to week 8, because you might see a little bit of emphasis on those weeks, right? In
Yeah.
this upcoming
Yes, sir.
exam,
Yeah,
and
yeah.
then the similarly for the interim, I mean, there's some time, but still the syllabus will be 1 to 8. Okay, sorry, 1 to 12. So whatever you're learning from 1 to 8 will be helpful in the interim exam also. That way. Okay.
Yes, sir.
Okay. So I think that uh, that concludes it. Anything else before we close, or otherwise close for today? Thank you so much for being here, and we'll see you in the next one. We'll announce the. I think the session, the problem solving one is not there on the calendar, but we'll announce it. Okay, before it, once it is scheduled.
Thank you, sir.
Thank you. Okay, then we'll close. Thank you so much for being here. Yeah, thank you.
Thank you, sir.